Hi guys, welcome all of you. This is Reena V. George from RVG Maths and Talents. Today we are starting Standard 10 CBSE Mathematics Chapter 1 Real Numbers. I think all of you like mathematics. If you don't like mathematics, or you have any dislike towards mathematics, you just try to understand it clearly, then you will definitely love it. Okay, so let us try together to love mathematics. Okay, let us start. See the first lesson, real numbers. See, in this lesson, fundamental theorem of arithmetic, then prime factorisation, a relationship between HCF and LCM, application of HCF and LCM, then proofs of irrationality of root 2, root 3 and root 5. Okay, let us start with natural numbers or counting numbers. So 1, 2, 3, 4 etc. up to infinity is the natural number system. So we denote natural numbers by n, and in natural number system we know it is 1, 2, 3, 4, 5 etc. It goes to infinity. Human beings expanded this number system due to their need, and this whole number system came into existence. Okay, so to form this whole numbers, we just added 0 to this natural numbers. And whole numbers are denoted by W. See, again, necessity demanded expansion of number system by adding -1, -2, -3, etc. to this whole number system. What we got? We got this Z, the integers. So integers consists of numbers 0, 1, 2, 3 etc. up to infinity, and -1, -2, -3 etc. So that is integers. Okay. Again, it is expanded. And we got rational numbers. What do you mean by rational numbers? See, rational numbers are numbers, see, that can be expressed in the form of P upon Q, where some conditions are there. P and Q are integers and Q not equal to 0. Okay. See the example 2 upon 5. That is a rational number. 2 and 5 are integers. Okay. And this denominator is not equal to 0. Then it is a rational number. Can you find any other example? See, 3 upon 4. Okay. See another example, 7 upon 1. That is 7, is it? That is also a rational number. That means any natural number is a rational number. What about whole numbers? That's also a rational number. See, you can write 0 over 7. That is 0. See, you can write 0 upon 9. What is it? 0 upon 9 is 0 itself. That means 0 can be expressed in the form P upon Q. That means whole numbers are rational numbers. And what about integers? That's also a rational number. For example, if you take -2, you can write -2 upon 1. That is equal to -2. That means -2 is also a rational number. Okay. That means all integers are rational numbers. Then numbers which are not rational numbers are called irrational numbers. Examples are root 3, root of 2, pi, etc. are irrational numbers. Okay. See this, rational numbers and irrational numbers together forms real numbers. Okay. We have studied all these. We are just revising all these. So, rational numbers and irrational numbers together forms real numbers. Okay. Then consider again natural numbers or counting numbers. Okay. We are considering prime numbers. Already we have studied that also. What do you mean by prime numbers? One and the same number are the only divisors of prime numbers. For example, see 2. 2 is a prime number. See, if you factorize 2, we can write 2 times 1. That means 2 and 1 are the only factors of 2. You can take 3. 3 can be written as 3 times 1. No other factors, is it? That means 3 and 1 are the only factors of 3. Then you can say 3 is a prime number. Okay. See, we have seen here that prime number is a positive integer that is divisible only by itself and 1. Okay. 5 and 1 are the only factors of this 5. That means 5 is a prime number. Then you can see 7 is also a prime number. 13 is also a prime number. Okay. Then you can see here 2 is the smallest prime number, and you can see that 2 is the only even prime number. See, these are all examples of prime numbers. 2, 3, 5, 7, 11, 13, 17, 19, 23, etc. In the case of 19, we can see 19 and 1 are the only factors. In the same way, 23 also can be written as 23 times 1, and then 23 is a prime number. Okay. Then next we consider composite number. We know that. What is composite number? See, we have seen that prime numbers have only factors itself and 1. Okay. But composite number should have at least one other divisor. Understand? Other than 1 and itself. See, for example, 6. 2 times 3. Understand? Then 2 is a factor, 3 is a factor. Definitely you know 6 equal to 6 times 1. Is it? 6 and 1 are factors. But we can see here that 2 and 3 are also factors. Understand? That means other than 6 and 1, we get other factors also here. 4, another composite number. 2 times 2. Is it? 2 is another factor here. 4 and 1 are factors, but we have other factor here. Is it? Such numbers are called composite numbers. Okay. So, composite numbers means it will have at least one divisor other than 1 and the same number. Okay. So, you can say every positive integer is composite, prime or unit 1. Okay. Another example is 21. 21 is a composite number. You can write 21 as 3 times 7. So, we have seen prime numbers, composite numbers and unit 1. See this, 15, 21, 27, 32, 36, 45, 55. All these are composite numbers. Okay. See, you can write here 15. See, 15 can be written as 3 times 5. So, you can say 3 and 5 are prime factors of 15. Okay, you got it? Okay, the next one, 21. See, you can write 3 times 7. See, you can see 3 and 7 are prime factors of 21. Okay. Then can you write this 27? See, we can write here. 27 can be written as 9. Or you can write 3 times. This 9 can be again factorized as 3 times 3. So you can say 27 can be written as 3 times 3 times 3. Okay. So you can write here 3 to the power of 3. Is it? This is prime factors of 27. Now let us consider natural numbers. See, we have written here this into 2 groups. Can you find what these groups represent? Can you find? Just observe it. Can you find? See, 2, 3, 5, 7, 11, etc. Can you say what it is? You know? 4, 6, 8, 9, 10, 12, etc. Can you say? It is composite numbers. Is it? Okay. So we can find 2 groups here. Prime numbers and composite numbers. Okay. See, we can write these composite numbers into prime factors like this. See, for example, 26 can be written as 2 times 13. And 75 can be written as 3 times 5 times 5. Is it? This can be written as 2 times 3 times 5 times 7. That is prime factors. Okay. What about 180? You can write like this. 2 times 2 times 3 times 3 times 5. That is 2 square times 3 square times 5. So these are all prime factors. Okay. How can we factorize this? See, 10 is written here. We are dividing it by 2 because we know 10 is an even number. So 2 is a factor. So dividing 10 by 2, we will get 5 here. 2 5s are 10. Then again 5 is divided by 5. Then we are getting 1. That means you can write 10 as 2 times 5. See, here we can do in this way also. 10 is divided by 5. What you will get? You know it is 2. 2 is divided by 2. That is 1. So you can write here 10 equal to 5 times 2. See, both are equal. See, we are not considering the order. We know that 2 times 5 and 5 times 2 are equal. Say, neglecting the order, we can say this factorization is unique. Okay. Then next consider another example. Factorize 30 into prime factors. Already you know that. Let us try together. Okay. You just do it. 30 divided by 2. What you will get? 15. It's not an even number. 2 is not a factor. So let us try 3 here. 15 is divided by 3. You will get it is 5. Then again we divide it by 5. Then you will get 1. Then how will you get here? 30 is equal to 2 times 3 times 5 times 1. So you can say 2 times 3 times 5 is the prime factorization of 30. Here we started with 2. But we can start the division by 5 also. See, 30 is divided by 5. Okay. You will get 6. 6 5s are 30. Okay. Then 6 is divided by 2. Then you will get 3. 2 3s are 6. Then 3 can be divided by 3. Then that means 30 equal to 5 times 2 times 3. So 5 times 2 times 3. That is the same as 2 times 3 times 5. Is it? Both are same. That means this factorization is unique. So all these are prime factors. Is it? See, already we are familiar with factor tree method. Is it? We have done that earlier. 30, it is divided by 2, we will get 15. 15 is divided by 3, we will get 5. then we can write 30 equal to 2 times 3 times 5. Is it? Tree method, factor tree method is familiar with us. Okay. See, 126 is divided by 2, then we will get 63. Again divided by 3, you will get 21. Again we are dividing it by 3, we will get 7. Then 7 is divided by 7, we will get 1. Okay. So these are the prime factors. So what are the prime factors here? 126 can be written as 2 times, 3 times, 3 times, see, 2, 7. Okay, so these are the prime factors. So you can write 2 times 3 square, 7. Okay, see, here we started with 2. See, we can do in another order also. 126 can be divided by 3. Okay, 3 4s are 12, 3 2s are 6. Okay, 42 can be divided again with 4 plus 2 is 6. 6 can be divided by 3. So again we can divide it by 3. Then 14. So we can divide it by 2. Then we will get 7. 7 is a prime number. Okay. So 7 can be divided by 7. We will get 1. So what are the prime factors here? 126 equal to 3 times 3 times 2 times 7. So this can be written as 3 square times 2 times 7. See, the same factors. Order is different, but you can say it is unique factorization. Is it? These prime numbers are the same. Is it? 3 square is here. So you can write here this in the same way. This can be written as, this 126 is 2 times 3 square times 7. Is it? So you can say the prime factorization is unique. Okay. See the factor tree method. See, 126 is divided by 2, 63 divided by 3, again 21 divided by 3, we get 7 here. So the factors are 2, 3, 3 and 7. So you can write 126 as 2 times 3 times 3 times 7. So that is this. Here we are doing prime factorization, and we can say neglecting that order, we can say factorization is unique. Next example, factorize 72 into prime factors. Is divided by 2, we will get 36. Again dividing by 2, we will get 18. Again divided by 2, 9. 2 9s are 18. 3 3s are 9. Again dividing by 3, 1. Okay. So what are the factors here? 2 times, 2 times, again 2, 2 times, again 3, then again 3. Okay. 2 to the power of 3 times 3 to the power of 2. That means 2 cube times 3 square. See, let us try. 200 divided by 2, we will get 100. Again, we will get 250s are 100. Then we are dividing it by 2, we will get 25. Again, we are dividing it by 5. 5 5s are 25. We are dividing it 5. Then we get 1. So what are the prime factors of 200? 2 times 2 times 2. So you can say 2 cube times 5 square. Okay. So these are the prime factors of 200. Okay. We have seen this. Then next comes 216. 216 is factorized like this. We are getting 2 how many times? 3 times. Okay. And 3 how many times? 3 times. Okay. We can do in this way also. That means we can start with 3 here. So let us do 2. Okay. Again 3. 3 2s are 6, 12, 3 4s. 3. Then 8. 2. 4. 4 is divided by 2. We will get 2. Again divided by 2. 1. So we are getting prime factors like this. 3. How many times? 1, 2, 3. Okay. 3 to the power of 3 times 2 raised to the power of 3. Is it? Both are same. So this factorization is unique. Okay. So here we can see the factorization of these numbers can be done in a unique way if we are not considering the order. In all these examples, we have seen that we are not considering the order. This prime factorization is unique. Have you understood this? This is unique. 2 cube times 3 cube and 3 cube times 2 cube. Both are same. Is it? Same value. And factors are the same. Here 3 is a factor, 3 is a factor, 3 is a factor. Here also we can see this, that factors. Okay. Here this 2 are factors, here also. That means this factorization is unique. Then we can say factorization of these numbers can be done in a unique way if we are not considering the order. So we can say that prime factorization is unique. So we are telling prime factorization is unique. See, that is theorem 1.1. Fundamental theorem of arithmetic. So we have studied that theorem. What is it? See, so far we have seen that prime factorization is unique if we are not considering the order. Is it? And we can see every composite number can be factorized into prime factors. Okay. So we can say every composite number can be expressed or factorized as a product of primes. Every composite number can be expressed as a product of primes. Okay. Then, and this factorization is unique apart from the order in which the prime factors occur. That is known as fundamental theorem of arithmetic. Very important theorem. Okay. So we have studied that. Is it? I think all of you understood this. Is it? The prime factorization of a natural number is unique except for the order of its factors. The same theorem. The prime factorization of a natural number is unique except for the order of its factors. See, here it is any natural number. See, for example, we are taking a natural number 5. Then 5 is 5 times 1. That is unique. Okay. It is 3 times 3. Okay. That prime factorization is unique. Okay. See, 9 can be written as 9 times 1. But that is not prime factorization, is it? So, if you take the prime factors, then we can say that factorization will be unique. Okay. I think all of you understood this. Next, consider this factor tree. See, we are factorizing this using factor tree method. Okay. Let us try together. See, 32760 is an even number. We can divide it by 2. Then dividing by 2, we are getting 16380. Okay. Again, divide by 2, we are getting 8190. Again, it is divided by 2, we are getting 4095. Okay. 4095. See, we start 3. See, 4 plus 9, 13 plus 5, 18. 18 can be divided by 3. So, 3 is a factor here. So, divided by 3, you will get 1365. Again, 1 plus 3 plus 6 plus 5. Then 15 can be divided by 3. So we are getting 455. Again 5 is a factor here. Divided by 5, we are getting 91. 91. Then we have to find the factors. 2, 3, 5, 7. Let us try 7 here. 7. 91 is divided by 7. We are getting 30. So you can write 32,760 can be written like this as factors. So we are getting 2 cube times 3 square times 5 times 7 times 13. Okay. So this factorization is unique. Okay. So it's very interesting. Okay. I think all of you understood this. See this. All these numbers are factorized. You just try for that. Do this factorization as you are on. You do this as homework. Okay. And I think all of you understood this. Okay. It's very interesting, I think. Okay. Then let us do in the next class. Okay. Thank you.